Welcome to The Explainer. Today, we're diving into a mind-bending April 2026 paper by David Garrison that honestly completely blew my mind. It takes basically everything we thought we knew about the absolute limits of classical computing and just flips it on its head. It's a conceptual heist, really. Garrison is essentially taking the secret mathematical sauce of quantum computing and running it smoothly on our everyday commodity hardware. So, here's a massive question. Do we actually need quantum computers to solve our toughest problems? For years, the conventional wisdom has been, well, absolutely yes. Right now, two of the most intensely demanding computing problems in the world are hitting severe, practically insurmountable bottlenecks. On one hand, training these massive AI models is scaling entirely out of control in terms of cost. And on the other hand, simulating quantum chemistry, like transition metal dimers, which are molecules with just incredibly complex magnetic interactions, causes our traditional computers to completely choke. We've been told over and over that only physical quantum hardware could save us. But what if that assumption is just completely wrong?
Here is our agenda for today. We're going to cover the computing bottleneck, stealing quantum math, how DTRN actually works, shrinking large AI models, solving quantum chemistry, and finally, rethinking quantum advantage. Let's jump right in.
Section 1. The computing bottleneck, dense AI and huge Hilbert spaces. Let's start by looking at the actual root of our computing nightmare, the quadratic growth of dense weight matrices. To put that into perspective, state-of-the-art AI training budgets are now blowing past 10 to the power of 25 flops. A single forward pass on a relatively modest 7 billion parameter language model, that demands roughly 100 trillion operations. You see, the standard unstructured dense layers that make up our neural networks scale at n squared. Imagine trying to map out a city where every time you build a new street, you're required to install a traffic light at literally every single other street that already exists. That n-squared scaling means we're hitting a very real wall of math and physics. Moving to Section 2, stealing quantum math, classical extraction of quantum efficiency. This brings us right to the core proposition of the paper. What if the efficiency of quantum computing comes from its math and not the physical hardware at all? The author noticed something brilliant here. Quantum neural networks get their insane efficiency from three very specific mathematical ingredients. Let's break them down real quick. First, tensor product factorization. It's kind of like breaking a massive, impossible puzzle into small, completely independent blocks. Second, orthogonality, which keeps your data super stable as it moves through the system. And third, partial trace dissipation. Think of this like a pressure valve that's constantly venting off unnecessary information. Garrison realized, hey, these mechanisms are individually classical. You don't need a freezing cold quantum chip to run them. So he literally just ported this math directly onto standard off-the-shelf GPUs. Which brings us to Section 3. How DTRN actually works. The Dissipative Tensor Rotation Network. This is the actual solution presented in the paper, so let's look at how it's built. This brilliantly lays out the architecture. Instead of just one giant, messy block of weights, the DTRN weight operator uses what's called a Kronecker product. If you're not familiar, think of a Kronecker product like mathematical Russian nesting dolls. It multiplies small rotation matrices in this highly structured, patterned way rather than just mashing them all together into chaos. Then, those matrices are passed through a learned dissipative bottleneck. That bottleneck deliberately throws out a fraction of the factors and replaces them with fresh ones, which beautifully mimics how a quantum system sheds information to its surrounding environment. Now here is the absolute kicker. By structuring the math exactly this way, this setup drops the parameter scaling from that massive n-squared curse down to a highly efficient n log n. To make that real for you, if your network has 1 million parameters, n-squared scaling demands 1 trillion operations. But n log n, that scales to just a few million operations. It completely breaks the mathematical gridlock we've been stuck in. Looking at this data straight from the paper, the impact becomes crystal clear. DTRN provides the exact same computational complexity as a fast Fourier transform. But what's truly wild is that because it uses those orthogonal rotation matrices we just talked about, it perfectly preserves the signal. Gradients don't vanish into nothingness, and they don't explode into chaos either. It trains incredibly smoothly using ordinary backpropagation, all with drastically lower memory and parameter needs. Okay, Section 4, shrinking large AI models, putting DTRN to the test.
Let's see how all this elegant theory translates into actual, hardcore machine learning validation, starting with computer vision.
On the CFAR10 image dataset, standard, unstructured, dense layers are, frankly, notoriously bad. But check out the performance line representing DTRN. It consistently crushes the dense MLP baseline by staggering 17 percentage points, all while using way fewer parameters across 3 separate random seeds. This is a massive leap forward in ML benchmarks. It proves beyond a shadow of a doubt that structured mathematical factorization is vastly superior to just brute forcing a giant block of n-squared parameters at your problem.
But guys, this right here is the absolute jaw-dropper, an experiment called Fast Micro Llama. By applying DTRN to a Llama class language model, the paper proves we can compress a 1 billion parameter model by 10.25 times. We're talking about shrinking the checkpoint down to roughly 1/4 of a gigabyte. This isn't just theoretical fluff. This is genuine deployment-ready efficiency. It means you could run robust enterprise-grade AI natively and smoothly right on the standard Apple M1 MacBook sitting on your desk, using less than 1 gigabyte of RAM. That is a real game changer.
Now, let's be real for a second. The paper adds some absolutely crucial nuance here that we need to pay attention to. DTRN isn't just magic fairy dust you can sprinkle on every single problem. When the author replaced all the dense maps in a transformer with pure DTRN, the model actually became unstable. But when applied as a hybrid approach, like combining it with CNNs to maintain domain structure, it heavily beats generic expressivity. The lesson is simple. You can't just treat every screw like a nail. You have to align the mathematical factorization with the specific structure of whatever problem domain you're tackling. Shifting gears to Section 5, solving quantum chemistry, a classical surrogate. Let's look at that second major computational bottleneck, simulating strongly correlated electronic structures. To put this to the test, the paper looks at the chromium dimer, or CR2. In the world of quantum chemistry, this is famously one of the hardest multi-reference benchmarks out there. And DTRN steps in as a classical surrogate here. It allows for stable, monotone variational convergence on the highly complex CR2 dimer natively on a single GPU. And get this, it does it without all the notorious headaches of actual quantum hardware. No complex trauterization approximations, no error-inducing shot noise. It just simply works at full machine precision. So why does this work so incredibly well? Well, this quote right here really nails the underlying physics principle. The DTRN's tensor factor bipartition enforces an area law entanglement cap by construction. In plain English, particles don't just infinitely entangle with every single thing around them in pure chaos. They obey physical boundaries. It's kind of like a juicy piece of gossip that only spreads to your immediate neighbors. DTRN naturally mirrors these entanglement boundaries, perfectly capturing the physics without wasting parameters on states that are mathematically impossible anyway. Bringing us to our final section, Section 6, rethinking quantum advantage. Cross-domain principles. Bringing all of this together across AI and chemistry, what does DTRN actually mean for the broader landscape of technology? The major takeaways you should absolutely remember from this explainer are super clear. First off, enforcing structural domains is essential. Structure will always beat generic n-squared expressivity. Second, unrestricted global rotations are risky. You really want local factorization first. Third, especially in chemistry, physically meaningful initialization is a strict prerequisite, not just a nice-to-have bonus. And finally, maybe the best part, DTRN is a team player. It's designed to compound multiplicatively. You don't have to throw away your standard transformers. It sits perfectly inside them, compounding with efficiency tricks we're already using, like mixture of experts, LoRa, and quantization. Which leaves us with this final, kind of provocative thought. For decades, we have been chasing physical quantum hardware to give us these exponential speedups. But if we can just extract the structural software of quantum mechanics, the tensor products, the orthogonality, the dissipation, and run it smoothly on our everyday laptops, what other classical breakthroughs are just waiting to be mathematically stolen? Thanks for joining me on this explainer, and I'd challenge you to take a hard look at your own computational bottlenecks. Could they be solved not by waiting for better hardware, but by leveraging better math?